Welcome back to the notes portion of our introduction to wastewater and wastewater treatment. Hopefully that last video that showed you some of the unique challenges facing wastewater operators from actions that we may take was informative. And as we move into this section, we're going to look at kind of the purpose of doing wastewater treatment. Also, how do we regulate wastewater treatment through the NPDES permits? And later on in this section, we'll get into the different types of wastewater treatment, like on-site treatment versus municipal systems. This first section is going to focus on municipal systems to a good degree because we're going to be focusing about NPDES permits first. But before we get into that, let's get into the purpose of wastewater treatment. So why do we treat wastewater? So to put it simply, there's always somebody downstream, and the Clean Water Act, particularly as passed in 1972, said that we are to make all of our nation's waters swimmable and fishable. So what about our drinking water? Where does our drinking water come from? So I'm going to go over that image there here in a second, but it's important for us to know that in Richmond, Kentucky, we get our water from the Kentucky River. The city of Irvine puts their wastewater effluent into the Kentucky River, and then we drink water from the Kentucky River. Our wastewater goes into Otter Creek. Otter Creek flows into the Kentucky River, and downstream from Otter Creek, the city of Lexington gets their drinking water. They also get their water from Jacobson's Park, but they also get a lot of their water from the Kentucky River. So there's always somebody downstream. So the quality of our surface water impacts our drinking water, whether that be from harmful algal blooms, from too much nutrients, or whether it be from sewage or pharmaceuticals. Our surface water for a lot of our nation, as you know from our previous section, over half of our nation gets their drinking water from surface water. That impacts our drinking water. And then our drinking water ultimately gets used and becomes part of our wastewater stream. And as it's discharged as effluent into like a river or a lake, hopefully or usually a flowing body of water like a creek or a river, that river is called the receiving water. The receiving water is somebody else's surface water after you get away from the effluent point. And we know that our water quality influences both ecosystem health as well as human health. And there is a strong relationship between these. And we know that our health is dependent upon also ecosystem health, just part of the larger One Health ideal. So moving on into this next section, we need to figure out how strong our wastewater is. You remember the two major measures of determining sewage strength are BOD and TSS. So BOD, biochemical oxygen demand, TSS being total suspended solids. And in many cases, the sewage coming into a wastewater plant is at least 200 milligrams per liter. How much oxygen is in water? So if you were out to go out to a lake, it can only hold like 8 to 12 milligrams per liter on a good day. So the demand for oxygen in our sewage is actually greater. It's actually greater than the amount of oxygen water can hold. So what makes that important from an occupational health standpoint? Well, when people are working around sewage, or when they're down in a lift station, or they're in a sewer pipe, if the demand for oxygen is 200, you could imagine what that might pull out of the atmospheric oxygen that might be in that sewer lift station or in that down inside that manhole. So people die from hydrogen sulfide poisoning and from not having enough oxygen. So total suspended solids equate to about 240 milligrams per liter. So it's a pretty good amount in our wastewater. So they put the sewage, you can put it into like a big cone and let it settle. They're settable solids, you can measure them. Suspended solids will actually settle out, and you can measure the height on this big cone, and it's got labels that can convert that value for you. So what impact would that BOD have on aquatic life? So the typical BOD for a wastewater coming into a plant. We call it the effluent. It might be 200 milligrams per liter. And again, it can be higher. Well, we know that oxygen at a typical water temperature may be anywhere 100% saturation for this particular temperature, whatever it might be, is about 10 or 11. If you shake the bottle up, you can get higher concentrations until the oxygen bubbles go off, but 100% saturation is right about there. So 200, that would use all the oxygen and leave nothing left, and still not satisfy or quench the demand. So why do we measure BOD? Well, we measure BOD to determine the sewage strength. We also measure it because it's required by law. It's a regulatory thing. So the Clean Water Act, as we said, requires streams and rivers to be swimmable and fishable, and we don't want them to be on the 303D impaired list. So how do we get folks to go along with the Clean Water Act or the Federal Water Pollution Control Act? How do we get them to do this? So the Clean Water Act is the name that's given to this act when those amendments were passed. We do this through the NPDES permitting process. And as you remember, the NPDES permits are the way that the states have told the US EPA that they're going to ensure that the Clean Water Act is being met. Clean Water Act established that NPDES system, the National Pollutant Discharge Elimination System. So why do we measure? Why do we measure BOD? Well, we know that a drop in dissolved oxygen in a stream would obviously be really bad, right? We can figure that out. It'd be bad for the fish. But a lot of things can cause a drop in measurable DO. And you can only measure DO like from 8 to 0 or from 10 to 0, or whatever the temperature of the water allows the DO saturation to be. So a drop in DO, well, what could cause that? Well, a lot of things could cause that. So speculation could be made by a drop in DO that it was the wastewater treatment plant. But somebody could also say, well, it's the cattle, or it's all the algae, or it's something else. So BOD is a more concrete determinant of the strength of the pollution. It's more long-lasting, and it's something that we can measure. All right, so the typical NPDES permits allow, in many cases, up to 30 milligrams per liter. These obviously can vary by stream quality and other, effluent sources or other people emitting wastewater to the stream. And BOD, to my knowledge, is almost every wastewater plant. I can't think of any that do not have BOD on their permit. Even industrial wastewater plants have to worry about complying with BOD. The BODs have been set a long time ago, and why we're going to use the BOD 5, and how the number 5 was used, it's not related to the work week, because once you set up the test and carry it out, it actually ends up, if you start on Monday, you won't finish until like a Saturday. So it's not for that 5-day work week reason. So why do we do it in 5 days? Well, the story that seems to have the most veracity or the most truth to it is in London, these water folks in the United Kingdom for the whole, UK determined that on apparently the entire United Kingdom or in England or whatever, if rain fell anywhere in the UK, all the water from those streams would eventually make it to the ocean within 5 days. So any effluent source, any pipe going into any of their rivers or streams would theoretically be able to discharge waste that would take 5 days to get to the ocean. And they didn't want anything over a 5-day period of time. Like if a slug of really nasty water was released and would take too much demand of oxygen that would cause like a fish kill, they didn't want, to take that risk. So if it can get out to the sea in less than 5 days, it may not be a problem. But on the island or the British Isle there, 5 days is how long, and they want everybody to be playing by the same set of rules. So that's why they apparently did it. All right. So why do we do this? Again, it's required by the Clean Water Act, and all the states require that. Measuring DO and measuring BOD, there's a lot of similarity. We have to do dilutions. And why do we do dilutions to measure our BOD? Well, again, like we're measuring actually the change in oxygen. So this will make more sense here in a second. So most BOD bottles are 300 milliliters in size. See what those bottles look like? Here's a BOD bottle. And what we're going to do is we're going to measure the change in dissolved oxygen in one of these bottles. And if you can only start off with like 10 milligrams per liter of oxygen and you suck all the oxygen out of it, then all you could measure is 10 milligrams per liter. So we have to do these dilutions. And based upon whatever dilution you decide to use, here's the range of the BOD values you can get. So you can, if you do 0.02 milliliters of sewage and 300 or 299.98 milliliters of water, this is the range of your BOD. So you can measure all the way up to 30,000 to 105,000. If you've got pure sewage and do no dilution, all you can measure is 0 to 7. Let's go back and look at the permit. Well, I don't think I pulled the permit. Yeah, I did. I gave you guys a picture of the permit. Typical MPDS permits are 30 milligrams per liter. So if you didn't do a dilution and all you had was a value that was greater than 7 because you exceeded your test, what would you report to the state? Oh, we exceeded 7? Well, my assumption would be, well, if you exceeded 7 and you can't tell me if it was 18 or 20 or 25 or 29, then it must be over 30. So we have to err on the side of caution of protecting public health and ecosystem health. So we use dilutions so that we can measure more things. We have to know our wastewater in advance or have an estimate about what our wastewater is going to be like, and also be prepared for bad days or days when the BOD levels might be a lot higher than we might expect. This will all make more sense as we put BOD measurement into practice. So these are BOD bottles. They got these special caps on them that hold the oxygen in there and don't allow the oxygen to escape during the test. So I've got this fake BOD bottle here. And when we do this in practice, these bottles are filled up. You will have a negative control. That is just pure water. Theoretically, there should be no microbes in it, be sterile water or deionized water. You will also have maybe a pure wastewater sample. It's just pure, either sewage effluent. Usually we're talking about effluent, but you can also measure the strength of your sewage coming in. So 100% sewage. And then you'll also have a dilution. Not just one, usually several. In this case, I've got 2. This one is 50 milliliters of the actual sewage effluent. You can see the 50 mils there. And then you add the 250 mils of your clean water. And then you'll mix it up. This one is 10% sample or effluent. And then it's 90% water. So we've got 4 bottles there. Negative control, 100% sewage, 6% sewage, 10% sewage, or 100% effluent, 6% effluent, 10% effluent. And then at some point in time, what we will then do is we will actually measure the dissolved oxygens in them using a dissolved oxygen probe. And I'll show you guys that here in a second on how this works. I'm going to stop this video here so that you have a break and we'll get back to it.